Welcome back, and in this lesson we're going to be talking about how to find primes, but this time we're going to be using Aristophanes' sieve, which is the best way we know of to find the number of primes from 2 to n. Now, if you ever watched our video on Euclid's GCD method, Aristophanes was another Greek mathematician, and he discovered this sieve in ancient Greece by hand. Again, fairly impressive considering the time frame. Now, the sieve is very space efficient, but it's far better time-wise. So our goal here is to basically make a very time-efficient algorithm, but the sieve is worse for space efficiency than the previous algorithms we've discussed for reasons you'll see. But with that in mind, let's look at the actual sieve itself. So imagine we start with a Boolean array of size n, where n is the value we need to go from 2 to n to find all the prime numbers in that range. And then we need to make sure we ignore 0 and 1 by rule, because 0 is always going to be a insignificant number for primes, and 1 is also ignored for prime numbers. And they're always going to be a special case, remember. So we start at 2, and then we go to every index of 2 that's a multiple of 2. So basically, let's say we want to find all the primes from 2 to 100. We start at 2, and we say, okay, every single index 2, or multiple of 2's index, we set it to false. The assumption here is that the array was initially set to true for all values. So we start at 2 and we say, okay, 2 is set to false, 4 is set to false, 6 is set to false, 8 is set to false, 10 is set to false, and so on and so forth until we hit 100. Then we finish up, and then we move on one more further. We then say, okay, we start at 3, and then we do the same thing for multiples of 3. So we say 3 is going to be set to false, 6 is going to be set to false, but 6 was already false, so we can skip over that. The assumption here is that if a number is, if the value at an index is already false, we ignore it. We won't try to reset it to false because it's already false, so don't waste your time. So we do the same thing for multiples of 3, and we keep on eliminating numbers. For multiples of 4, we already checked multiples of 2, so we don't need to bother checking. Again, if the number we reach at an index is already false, we ignore it and we don't do this step. We don't do the multiples of I and then keep going until we hit the 100 or top end of the range. So basically we keep incrementing our value until we hit n, or the ending value of our index. The most amazing thing about how this works though is that it's so efficient, because initially we start with 2, 4, 6, 8, and so on and so forth. We'll cross out half the possible values. That means that we don't have to do the multiples of 4, multiples of 8, multiples of 16, ever, because we already did all the multiples of 2. So by doing the multiples of 2, we drastically cut down the amount of work we have to do in the future. But it's not just like we're doing it for even numbers, we're doing it for all odd numbers too, or multiples of an odd number, like 3, like 7. All of those are going to do the same thing. The advantage here, though, is that if we hit a number and it's not already set to false, we know it's prime. So for example, if we started out at 2, we know that 2 is prime, so we can when we hit 2 first, it's our first value we start with, it's initially set to true. So it's prime, and we can add it to a list. Then we set it to false and all of its multiples to false. But then we go to 3. 3 is not even, so it wasn't set to false before, and so 3 is prime. We add it to the list of prime numbers, set it to false, and do the same thing for all its multiples. 4 was already set to false when we did the run through for 2. So we ignore 4. We don't have to do the multiples of 4. We simply skip to 5. Well, 5 wasn't already set to false, 5 is still true. So 5 is added to the list of primes, and then we do the multiples of 5, 5, 10, 15, 20, and so on and so forth. So the way this works is that every single time we reduce the number of values we have to check the multiples for. And by doing this, we drastically cut down the amount of values we have to check overall. This is what the sieve basically does, and it makes it so much faster because every single time you're cutting down the number of values by the number of multiples a number has in the range. And by starting at 2, we initially eliminate the most number of values possible. The sieve is actually very easy to implement, and it works efficiently through the values. It's pretty much as efficient as possible for a reasonably quick implementation of prime number discovery, and it'll work on any type of system. Many of the more complex prime number discovery methods require multi-threaded or even multiple systems to work together in supercomputers. Ours will work well on any type of computer. The space complexity, though, and we're going to talk about the space complexity first in this case, is linear, because for every additional value we add to the range, we need one more space. If you start at 100, you need 100 spaces because you need to go from 1 to 100. If you go to 101, you need 101 spaces. That doesn't mean you have to do as many checks because many times that top value will already be eliminated by one of the multiples. But you still need more space. Remember, space complexity is another type of efficiency we care about. This is good for now at a space complexity of linear time because space and memory are much cheaper, as we've discussed, than time itself. But when you're working with extremely large numbers, this can be a problem. However, most of the time, because space is so much cheaper and easier to manipulate than time, we ignore it. The space factor really only becomes a problem on consumer systems when you're dealing with 10 plus digit values, because at that point it requires so much space that many times the memory won't be able to hold it. However, because of the way that the sieve works itself, and the way it reduces the number of potential primes so much each time it runs, and we greatly are able to build up that list of primes quickly, the time complexity is far better than any previous version we've talked about. Just to summarize, the time complexities we've seen so far were linear, then n log n for the modified brute force version, but this complexity is big O n square root n over log n. Now you might be saying, what does that really mean? Well, before we had n log n. N log n is fine, but n square root n is even better. Because while log n is a lower number than n square root n, just because of the growth rates we talked about before, by dividing it by log n at the end, we again cut down the time complexity significantly, and therefore the sieve is the best way to find the prime numbers out there. So this is far better than the previous complexity we talked about, and therefore the sieve is the optimal method we should use. As a quick little side note, I apologize, this should say n log n. So the time complexity, if you recall, of the modified brute force version, just as a verification, is n log n. That's just a typo, so ignore that. But n square root n over log n is a much, much better time complexity than n log n. So we should make sure that whenever we are trying to find a list of prime numbers from 2 to n, we use the sieve. So hopefully you enjoyed today's lesson. In today's lesson, we talked about the sieve of Aristophanes. We talked about how it works, how it's a fairly space-efficient algorithm, but not entirely space-efficient because it's linear time, or linear space efficiency. And then we talked about the improvement in time complexity that we have because it's n square root n over log n, which is always going to be better than the n log n of before. Hopefully you've enjoyed today's lesson, and hopefully you'll join us for our next lesson.